surface of the star gravitationally collapsing when it reaches a radius of 2m, which is the formation of a horizon. Singularity of r equals 0. And we had, so this is U going here, this is V, U is an effect parameter along sky plus, V is an effect parameter along sky minus. And we can define some modes here. Which behave just like plain spherical waves. And so these guys define some vacuum state, some quantum state, which is an Minkowski vacuum state at very early times, at t equals minus infinity. Similarly, you can have modes. I think I call them phi out, which are just spherical waves purely outgoing to sky plus. And they define, similarly, they define some out vacuum. This is the Minkowski vacuum state and sky plus. Okay, I call them phi out. Sky minus is a Cauchy surface. Sky plus is not a Cauchy surface. So you need to define some modes here. We call them Qs. Okay. So H plus together with sky plus, that's a Cauchy surface. And sky minus is a Cauchy surface. So the Q's are such that Q together with phi in here, Q's together with the phi outs and the complex conjugates, we form a complete set. In here, we have the phi ins and the complex conjugates, they form a complete set. And so you can look at the Bogoliubov transformation between one set and the other set. And that's, we found that the betas in the Bogoliubov transformation are non-zero. In fact, we found that the number of particles, so we've looked at late times, okay, for U large, and U large on sky plus. You look at the Bogoliubov transformation, so the betas in the Bogoliubov transformation is the number of particles that this vacuum state contains, the number of in-particles that this vacuum state contains on sky plus at late times. Late times I mean U. So at late times of sky plus, the number of in-particles in the out vacuum state, that's per unit time, is is the Hawking radiation. So you've got a thermal. So this is a black body type of radiation, thermal radiation. The temperature, the Hawking temperature, is given by kappa over 2 pi Boltzmann constant. If you remember, kappa is 4m, inverse of 4m. And this gamma is the gray body factor. So it's not quite black body radiation. This is the reason why it's called gray body factor. This depends on the frequency. So this distorts you a little bit away from just a pure black body spectrum. It also is such that this infinite sum converges. Okay? So this guy comes from the backscattering. The backscattering. Remember, the gray body factor was proportional to the reflection coefficient in the radial solutions. So if there's no reflection coefficient, if everything's transmitted through, nothing is backscattered, and you would actually get an infinite, a divergent sum here. So you should be shocked. People were shocked when this came up. This really is coming from, in here we've got Schwarzschild space-time, but as the star is collapsing, we've got dynamical evolution there. It is this dynamical evolution that's giving you creation of particles. This is related to the fourth thing I did in the course about the harmonic oscillator, whenever there is a time dependence in the force, then you get particle creation. This is the quantum field theory in coarse space-time equivalent of that. Now, that is expected that during a dynamical evolution there is particle creation. What is shocking is a black hole is created, it reaches a stationary state, Schwarzschild black hole, and yet you do have particles. The reason is because of this infinite redshift of the particles move away from the black hole to the described loss. So the particles remain there until the end of time, even though you've got a stationary black hole. So that's the first shock. The second shock is that it does not depend on the details of the collapse. Just pure, almost black body terminal radiation. So these were the two shocks that Hawking samplers introduced. Any questions about this? So just to give you an estimate for what happens for astrophysical black holes. So the Hawking temperature is 10 to the minus 7. Here I'm restoring units. So you've got 10 to the minus 7, the mass of the sun divided by the mass of the black hole, and this is much less the CMB temperature for astrophysical black holes. Very hard to detect, in fact. Impossible if you wish. If we had primordial black holes, that would be a different matter, but we haven't detected primordial black holes, so that's not the case for any black hole that exists, as far as we know. And so the Hawking radiation is taking away energy, and so energy is equivalent to the mass. As it takes away the energy it takes away, the mass is reduced, and so we say that the black hole evaporates. Okay? The mass of the black hole reduces due to the emission of Hawking radiation, so that's what we call evaporation, black hole evaporation. So you can get an estimate for the lifetime. Okay, so you have the black hole area is, I'm just doing estimates here, is proportional to the square of the mass, which is in the case of Schwarzschild proportional to the mass square. The Hawking temperature goes like 1 over the mass, so to the 4 it goes to the n to the minus 4, and then we just apply Stefan's law for a black body. From Stefan's law, you have that the luminosity, the flux of energy, I'm ignoring a constant factor here, it goes like the area times the temperature to 4, so that's m to the minus 4, and that goes like m to the minus 2. Okay, so as the black hole is getting smaller, the temperature is getting larger. Indeed, Hawking's first paper was called in Nature, 1974, was called Black Hole Explosions with a question mark. Explosions because of this, question mark because not even he could believe that he was trying to not be too assertive. So we're just doing orders, estimates here, so you can integrate this. So the lifetime just goes like m cubed. And then you restore the units. And so for a black hole of the mass of the sun, the lifetime is a lot larger than the age of the universe. So 10 to the 54 times the age of the universe. So it's going to take a while for them to evaporate via the emission of Hawking radiation.
What is that time? According to which observer?
I suppose this is just this is Schwarzschild time, which is an observer, inertial observer at infinity. This is indeed the temperature seen by such an observer. Any other questions?
Mark, you said about primordial black holes.
Yep.
What temperature we expect it to have?
Primordial black holes is kind of is your guess, but it would be detectable temperatures. Let me see if I have I think it was Hawking who also had a paper on this. Yes, we do have an estimate for primordial black holes. (10 to 15 grams), and so Hawking temperature 10 to the 11 Kelvin, which is certainly detectable. Okay, so that's the derivation of original derivation by Hawking. It was done exactly like we've done it here, so via considering a dynamical space-time and seeing how the results, this harmonization result does not depend on the details of the class. Now, there is a more manageable way of doing things, which is to look at eternal Schwarzschild spacetime, the maximal analytic extension of Schwarzschild spacetime, and doing modes that model, try to simulate the collapse, try to simulate this. So that's what we're going to do next. So it's quantum states. Our internal Schwarzschild spacetime. So we did already, I went through the whole derivation of the maximal analytic extension of Schwarzschild spacetime. So, a reminder, this is Schwarzschild. Singularity to the future and to the past. This is the future event horizon to the right, the past event horizon to the right, future event horizon to the left, past event horizon to the left, scribe plus to the right, scribe minus to the right, scribe plus to the left, scribe minus to the left, I minus to the right, I minus to the left, I plus to the right, I plus to the left, space like infinity to the right, space like infinity to the left. B is the bifurcation to sphere and reflection through. So this is what we call U bar, and this is what we call V bar. Reflection through the two sphere is just changing reflection through the two sphere. Bifurcation two sphere is just swapping, changing the sign of U and V, and by the omega I mean theta and phi. You leave the angles intact. We call this region 1, 3, 2, 4. 2 is the black hole, 4 is the white hole. Nothing that goes into the black hole can reach scribe plus. And anything in the region 4 will leave if you wait for long enough. And a Cauchy surface can be a time at t equals constant hypersurface, and this is an r equals constant hypersurface. Okay. So now we're going to define modes on this spacetime. So let's define the E modes, which are essentially the ones we've already seen. So to the right, So the in modes are just purely these modes. They're coming out, they're the same as the ones they defined earlier on. They define the in vacuum state, the Minkowski vacuum state at early times. They're coming out from sky plus to the right. They're just, they only have support on the right wedge, on the right region 1 of the space-time, outside the black hole. So they're coming out from sky plus, part of them is reflected back to sky plus. They're coming out from sky minus, part of them is reflected back to sky plus, part of them goes through to the horizon. So the important thing is Cauchy initial data. If you're just looking at the region 1, Cauchy initial data is purely outgoing from sky minus and 0 on H minus. So 0 H minus. Zero H minus, pure outgoing at sky minus. There is a reflected part that goes to sky plus, and there is a transmitted part that goes through to the horizon. This just comes in from the radial part of the radial factor in the modes. Okay? Remember, if you look at the potential, the radial potential, you had a wave coming in, part of the wave is reflected back, so that would be your A factor, and then part of the unit amplitude coming in, transmitted amplitude coming out. Okay, so all this is region 1, but in region 3, they are equal to 0. So this is asymptotic, this is not asymptotic, this is phi in or x is exactly 0 for any x in region 3. Okay? This is not an asymptotic relation, this is an asymptotic relation. Okay, you can define more modes, the up modes. So the up modes are going to be these modes. They're coming out from H minus, part of them goes through to sky plus, so that's going to be A up. And part of them is reflected back to the horizon. Sorry, the reflected part is A, and the transmitted part is B. That's our notation.
So, IP modes.
Up.
Modes.
Upgoing. It's short for upgoing. In is short for ingoing.
Yeah.
So let's be more precise about this. Asymptotic relationship, you've got some normalization constant. And as I say, period going from coming out from the horizon, the pass horizon, and note that all you need is the Cauchy initial data. All you need here is to give this. This is a consequence of this. You give initial data, you solve your wave equation, and find the value of the field everywhere. This is Cauchy initial data for region 1. Okay? Cauchy initial data for region 3 is just 0. Cauchy initial data for region 1 is given by this. This is, H minus R union scribe minus R. That forms a Cauchy surface for region 1. Cauchy surface for region 1 is this. You solve, to give that initial data, you solve your wave equation, and that gives you the value of the field everywhere in region 1. In particular, it gives you the value of the field arbitrarily to the future. You could do the opposite. You could give initial data on a Cauchy surface which is scribe plus R union H plus R. You could give initial data. You could give Cauchy data, characteristic initial data, in here, evolve the field backwards, find a solution for the radial solution, and therefore for the radial equation, and therefore for the full wave equation, evolve it backwards. You will find the value of the field everywhere in region 1, and in particular also at t equals infinity, at h minus and square minus. Similarly here, that's your Cauchy initial data. Okay, you give initial data here and here, and then you evolve, you solve the field equations, and you find that the future they behave like this. So this really is a consequence of the Cauchy initial data that you've given. This is in region 1, and again in region 3, they're just equal to 0. Now you can go over to your radial D, which is the second order linear ODE, and you can look at the Vronsky relations. You can look at the Vronsky between two solutions, in and up, in and in star, up and up star, all the combinations you want of two linear independent solutions of the radial ODE. So Vronsky conditions for solutions of the radial V. And there's a few of them. The ones that matter or that we care about are these two. Clearly, because of the complex conjugates we're doing here, we're looking at the Vronsky relations between the in solution and the complex conjugate of the up solution. And so exercise and their orthonormal modes so phi in R is normalized in this way. You determine any, so that this is true, and just the same as what we gave before, 1 over the square root of 4 pi omega. And same for the odd modes. This is also true for the odd modes. Okay, so phi in with phi up, do they form a complete set?
Yes. You have said that phi in and phi out, or phi in, phi out, phi in complete set.
Not out, up.
Up. Yes.
Phi in and phi up, do they form a complete set? And the complex conjugate of those, do they form a complete set?
In the first region.
Exactly. Only in region 1, they're equal to 0 in region 3. So they form a complete set of solutions. They can give you any value, any solution of the field in region 1, but not in region 3 because they're equal to 0. And so any linear combination of those will just give you 3 in region 3. It'll give you 0 in region 3. So,
Mark, but if you apply that thing that is to the bifurcation, and apply this in those equations, and you're finding the same expression, and but apply this would in your complete set in the region.
yeah, so that's exactly what we're going to do. That's exactly what we're going to do. But note that as we've defined the modes, we haven't done homogeneous yet, we're going to do that now, but as it stands right now, they're just equal to 0. That's why we call them R here. We just, they're equal to 0, the left region, region 3. So phi in and phi up and the complex conjugates form a complete set in 1, but not in 1 and 3. So we'll do exactly what Cassie just suggested, to get modes that are complete in the full region. So we apply exactly this. So we'll call them in and up, we'll call them left, comma L for left, and just the definition is that they are the same as the right ones, but complex conjugation and then minus u minus v, and the angle is just left the same. Sorry, this is R. So in particular, that means so the value of the L modes is equal to the complex conjugate of the value of the right modes in the reflected point. So the value of the left modes here is equal to the complex conjugate of the value of the right modes here. The value of the right modes here is equal to 0, like that. It's equal to 0 everywhere in region 3, and so that means that the left modes will be equal to 0 everywhere in region 1. So this implies that the left modes is equal to 0, are equal to 0 in region 1, obviously for any mode it looks.
Mark, you are conjugating because there's a minus sign when you take the internal product, right? Between those states in left. But why does this sign shows up?
Which sign?
You're taking
Yes, I think, so remember that, you know, dt goes in this direction here. In here, dt goes back down. So when we take the scalar product, you have to do it with respect to a normal going to the future, so with respect to minus dt. So the sign changes in the derivative that appears in the scalar product. And if you do the complex conjugate, you're going to get a minus sign here, and then when you move it to the other region, you want to make up for that.
Thank you.
So yes, so that's a very important thing. So that's phi in up left is the orthonormal. Okay. And now we do have a complete set of modes in the whole of 1 and 3. So phi in left, up left, in right, up right, and complex conjugates, and you have to go over all the indices. These guys form a complete set. In 1, in 3. And so, in particular, along a full sheet surface of a full space-time. So you can expand the field in these basins. Remember that we folded up the omega integral. When I say for all lambda now, I mean positive omega. Expanded in this business and the complex conjugate or Hermitian conjugates. And now you can define the vacuum state or a quantum state. It's called the polar state is defined by it's a state which is annihilated by all these annihilation operators. So the Holmer state P is defined by this. So sorry? Bowler. B-O-L-W-A-R-E. Bowler. So, question, this is equivalent, this is the black hole equivalent of which state in flat space-time, in the whole onboard effect set? Minkowski? Why Minkowski?
Well, I would say because you are getting modes from the infinities and you are very far away from the black hole. So basically you are, as you part, I would say that you are in the flat space-time region of the space-time.
But we're defining them here as well.
Yeah, this is
They're equivalent to the U modes.
Sorry?
To the U modes that we defined separating the two wedges.
U modes.
The U modes.
Oh, the U, you mean, yeah, the little U modes. Forgot they were the
Equivalent to the Minkowski modes, but separating the wedges.
okay. So did they define the Minkowski state or the Riemann state?
Sorry?
Did they define the Minkowski state?
Minkowski.
Okay, so you think Minkowski as well. Why do you think Minkowski? Okay. These are defined, this state is defined using modes, which are positive frequency with respect to one time.
DT.
T. T is the proper time of which observer?
Inertia.
T is the proper time of which observer?
to the
Sorry?
then you are within infinity. Inertial solving of that thing.
What type of observer? Let's forget about infinity. An observer here, finite radius. What type of observer there has T as its proper time?
Inertia. Inertia.
So the word inertial usually is for flat space-time. So I think the equivalent of inertial is free-falling.
Okay.
Why for the free-falling observer?
Why for a free falling? Because the free falling observer is following the physics.
Yeah. Why is its proper time T?
Is observed. T is the proper time of the observer that's following the geophysics.
Why? Why do you think that? Sorry, Paula.
Because the 5 parameter has T.
Define parameter along what?
Along like this in this direction.
Yes. Along which word line?
Geodesics
Which geodesic?
like this.
You're talking about this?
But at the point of this.
You're talking about this?
Yeah.
Who says this is a geodesic? This is not equals constant, right?
Then he's accelerating.
Why is it accelerated?
This isn't a geodesic.
Why is it not a geodesic?
There's a radially observer that just do not have angular momentum at infinity, it's falling straight inside the black hole. You fall inside the black hole.
Yeah. So, if this is the word line of an observer that just a constant radius is not, due to the gravitational field of the black hole, you should free fall into the black hole. That would be a geodesic. But he's not, he's just fixed radius. He has an engine, if you wish, that moves him away from the black hole, so he doesn't fall into the black hole. So that's an accelerated observer. So I agree with you. T is the proper time of such observer, but that's not a free-falling observer, it's not a geodesic observer. It's a static observer, therefore it's an accelerated observer. Therefore, what vacuum state is associated with the proper time of an accelerated observer in flat space time? Green one, exactly. So defined using modes that are positive frequency with respect to ddt, and t is the proper time, of a static and therefore accelerated observer. Okay. Now a way to look at this is you have, if it's static, ds squared is minus 1 minus 2m over r dt squared. That would give you the proper time minus the, so the proper time would be, r is constant for a static observer, so tau would be proportional to 1 minus 2m over r t, proportional between, r is just constant, so that factor is just a constant. Okay. So that's one vacuum. We still want the equivalent of so if you wish, Bohr is kind of the equivalent of the Wheeler vacuum in flat space. We still want to get the equivalent of Minkowski vacuum. Now, what we're going to do now is use modes that model the gravitational collapse. There are modes in the maximal analytic extension of Schwarzschild spacetime. All these modes now are on this background spacetime. The background spacetime is not a dynamical gravitational dynamical spacetime due to gravitational collapse of matter. They're in this spacetime, but we're going to define modes that model what happens to modes in the gravitational collapse spacetime case. So in the case of the spacetime of gravitational collapse, phi in as chi minus, remember we derive this well, the relationship between these modes and the out modes and chi plus. So this log or exponential behavior was the crucial thing. So we could have done the same. So this was sorry, this is chi minus. This was, we got this by tracing back the mode at chi plus, which was just purely outgoing to chi plus. It was the exponential of minus I omega u at chi plus, and we traced it back, reflected through r equals 0, going down to chi minus, and that's the relation, that's the form that we found for this mode there. We could have done the opposite. We could have started with mode, with this mode that's chi minus, and follow it through, reflect it through r equals 0, and taken it up to chi plus. This came from doing this. This came from doing this. And we could do the same thing by doing this. Just taking this mode and taking it up here. So we could have done similarly. But instead, tracing backwards. But instead of tracing backwards, phi out from chi minus, from chi plus to chi minus, we could have started with this as chi minus and trace it with the future. We would have found so you've got, we've got the relationship between u, so we've got u and v here. So we start with a v0, and this is u of v0. So we want to know the relationship between this value of u and this value of v. So we already found this. I'm using K and kappa. Okay, just make sure that's kappa, that's K. Kappa is the surface gravity, 1/4m. K is K1 times K2, constant of integration that are physically meaningless, depending on details of the clamps.
So there, in the upward explanation of my desire.
Oh, I'm going to do this now. I'm going to write it. I'm going to finish it now. So now, that's what I put in here. So the value of V will be this, V0 minus kappa U K. And this is for large U. Remember, we're doing this close to the horizon. So V0, by the way, is the one that generates the horizon. So V0 is actually this one. And this is U of V. Okay, for a given value of V close to U V0, what is the value of the corresponding value of U? And that's the relationship. Now, that's just related to the critical coordinate, capital U. So this is just K times, I'm distinguishing between little u and capital U. Capital U is the critical null coordinate. Which is defined in eternal Schwarzschild spacetime. Eternal Schwarzschild. So we can model such a mode escapes the star. Just about escapes the star. By using modes. So that V0 part is just a constant, you can just totally ignore this. H minus. And these are, which are positive frequency, with respect to the affine parameter on these modes in eternal Schwarzschild spacetime have a relationship between the affine parameter on H minus, so H minus would be this in the dynamical case. So these modes escaping reflected at R equals 0 just close to H plus. These modes that give rise to the Hawking radiation at late times on sky plus. The relationship between the fine parameter here and the affine parameter here is that happens in the dynamical case. Okay, there's the relationship between the V would be here, affine parameter here, but that's just linearly related to the affine parameter here. So this relationship, exponential relationship between the affine parameter here and the affine parameter here, or the affine parameter here and the affine parameter here, in the dynamical case is modeled, is the same as there is between these modes defined like this on H minus and the affine parameter on sky plus. The relationship between capital U in the eternal Schwarzschild spacetime and little u is just the same as there is between the behavior of the modes in a dynamical case, just as it's reflected at R equals 0 and sky plus. Okay, so the point is, now we're defining modes, which is our positive frequency with respect to capital U. Okay, not with respect to little u or little v. Those were positive frequency with respect to t. Now it's capital U. Okay, so we can look at the Bogoliubov transformation between these modes and the previous modes, the in and up modes. So we wish to find the Bogoliubov transformation between the modes that are positive frequency with respect to u and those that are positive frequency with respect to t. Follow what we did for one effect, which is we're going to find that some of it we're going to do the same way, some of it we're not. So we'll write a linear combination of the modes, of the in and out modes, and we'll show that that linear combination is indeed positive frequency perspective capital U. So instead of using modes, the ones that I just described here, instead of these ones on H minus, we consider the following linear combinations. So phi up in capital letters and phi lambda up in capital letters R. So it's the same factor. And that just same thing but swapping L and up, L and R. So this is for all lambda, and for all lambda that means omega, this for omega positive. So this is, if you remember the Unruh effect, this is very similar to the the relationship that there was between the U modes and the phi modes. Recall transformation between the U's and the phi's. One more effect. Okay, so now we're going to do this in a different way. I'm going to prove that these modes are also positive frequency with respect to capital U. And so they define the same vacuum state. Okay? You can take any linear combination of these guys, as long as you include complex conjugates, that will give you some other modes that define the same vacuum state as these modes. All you need to show is that they're positive frequency with respect to capital U. If they're positive frequency, if these modes are positive frequency with respect to capital U, then it means that in the transformation between these modes and these modes, there is no complex conjugation. If there's any complex conjugation, you would be adding some negative frequency modes. And so they define the vacuum state. The advantage is now you readily have the Bogoliubov transformation between modes which are positive frequency with respect to capital U and modes which are positive frequency with respect to T. So you already have the Bogoliubov transformation. Yeah.
In the case that relation was omega minus omega, something happened here. Then the psi L, it was minus omega. There was kappa minus kappa, sorry.
Yeah, it was.
Something like that.
Well, yeah, that was that K, not capital K,
Yes.
that K. So we've changed, sort of in the index notation, we've changed things a little bit. That K. So one difference is we were doing Cartesian coordinates there. We're doing spherical coordinates here. So that K was linked to X or Y, we called it. Cartesian coordinate, spatial coordinate Y. And we had two, flat space, it was two-dimensional flat space as well. We had two scribes. In here, the lambda corresponds to spherical coordinates, so we have L, M, and omega. Now the omega here we've already folded up the frequencies over omega. That's why every time I say lambda, I mean positive omega. So we're in here, we're just doing positive omega all the time. In there, K was spanning the whole realms. So in terms of the index notation, we've changed things a little bit. Okay, so I still need to show, I'm claiming that these modes are positive frequency with respect to capital U. So these ones clearly are, okay, capital, you take the partial derivative with respect to these modes, and this is just minus I omega kappa and themselves. Okay. So when we say positive frequency, we mean excluding the minus I, because you would want to be doing I times this. So I times this would just kill this. And this is positive. This is positive. Omega is positive. Kappa is positive. These modes clearly are positive frequency with respect to, or another way to look at this is you just take the Fourier transform of this, and that will just give you 0 as long as omega is positive. So it will only give you support. The Fourier transform of this will only give you support, at omega, at the frequency which is omega over k, which is positive. So you want to show the same for these modes here. Okay? And as I say, the big advantage is now this gives you readily the Bogoliubov transformation. So phi lambda up and up are positive frequency with respect to capital U. Jesus, reorganization situations. Okay. So, phi lambda up, if we go to, sorry, there's a positive frequency with respect to U on H minus. So let's look at the values of these modes on H minus. So I'm ignoring this was on H minus, and this was on well, these are scribe plus and minus. So these guys, okay, so this factor here plays no role, so just put the square root. Phi lambda up, right. So this is exponential of I omega kappa log of minus kappa. And this is what I wrote down order. Now, this is only true. That's the value. That's the asymptotic value of phi of r. R means it only has support in the region 1 because it's equal to 0 in region 3. So region 3, this is u of r, but also capital U is positive here, capital U is negative here. So we want to indicate that's only on that's only for U negative. That's only true for U negative. So we want to put the theta minus 0. So this is the behavior of phi lambda up R. And then the behavior of these guys, well, you just look at the behavior of the R modes, complex conjugated, and change. Sorry, the L complex conjugated modes is just equal to the right modes swapping, changing the sign of capital U and capital V. So all you do is you look at this and change the sign of capital U and capital V, which is just changing the sign of this. So this is I omega kappa log of capital U. Okay, so this is phi up left complex conjugate. And this is only in the region 3. So this is only sorry? Sorry? Yes, exactly. Theta, this is only true for what I was thinking is I haven't really written this correctly because I'm really looking at this. So this is probably V goes to 0. And we're looking at the behavior as for all real capital U.
Okay.
And then we're still missing, so this is the radial part of the modes. So this is asymptotic but also proportional. Again, ignoring, there's the Y LMs and ends and the R. But this doesn't affect anything. All I'm interested in is the frequency behavior. Okay, so this is not going to affect any frequency behavior when you do the Fourier transform. I want to do the Fourier transform of this and show that it's only non-zero whenever for positive frequencies. So this is Now I'm going to appeal to a lemma that's written in a book, the book by Frolov and Novikov. So the lemma, so the proof of this lemma is in Appendix H of the Frolov and Novikov book that I recommended at the start of the course. So the lemma is this. That this is 0 for all p positive and for all q real. Now note that if you call this f of u, capital U, this gives you, this is just a Fourier transform of f. You're integrating with respect to the timing quotes, capital U,